and yang or other things like that. So, all right. So what I'll cover here in the next 30-40 minutes is going over what waves are and how we describe them and how we model them. And of course, one of the reasons why we're working on waves here is if you just look at, there's no big waves today as you see in the forecast, but if it gets wavy with the currents coming in and out of the channel here, it's just beautiful to look at. So we get kind of nice picture of waves over currents. And so there's a long tradition of working on waves here in the West. And actually, one of the fathers of numerical wave models was Robert Helsi, and actually used to work here back in the 70s, 80s. He's a developer of the DSA model, the first numerical model in the world that was developed first in Morocco and then here. All right, so waves we'll characterize them with these time and space scales, and I'll go through all that and get into what wave spectra are and what they look like. So I just borrowed this very classical picture from Walter Munk. If you go over different time scales of the waves, going over this axis here, with the wave periods going from a fraction of a second to 3 hours and a day, we have this kind of spectra. It's not to scale, it's just to give you an idea. Of course, we have the very long surface gravity waves are tidal waves driven by the gravitational pull of the sun and the moon. And the intermediate scales of a few minutes, these are typically tsunamis, and meteo tsunamis are driven by storms that can be at rapid changes in the wind, and this is what is called meteo tsunamis, and that give an oscillation of the sea surface of a fraction of a meter. In equatorial context, like the Risaga in Ciutadella Harbor in the Mediterranean, you can get a couple of meters inside of the harbor because of special resonances. And of course, the tsunamis are driven by earthquakes and landslides and other things like this. Everything else here of shorter periods is essentially driven by the wind. And this is what we'll talk about. These are our waves. Some of the waves are driven directly by the wind, and typically these go to wave periods of about 20, 25, exceptionally up to 30 seconds. Okay, these are the ordinary wind waves. Walter Munk introduced some difference between the gravity waves and what he called the ultra-gravity waves and the capillary waves, and this has to do with the effect that at very short scales, it's not just gravity that is a restoring force for these waves, but also the surface tension. And the transition between the dominance of gravity to surface tension occurs at a wavelength of about 1 centimeter or so. So and in the dispersion relation, that corresponds to a minimum of a phase speed, and that minimum phase speed is 20 centimeters per second for clean water. So I will not talk too much about these capillary waves and the very ultra-gravity waves. So we tend to go up to 1 second, 1 hertz, and not too much towards the higher frequencies. But then what I will discuss a bit more is this interesting region of what's called long waves or infrared gravity waves, which are typical periods between, say, 30 seconds to a couple minutes, and actually dominate the records of surface oscillations when you look at periods, yes, between 30 and 300 seconds. The mechanism for generation of these infragravity waves is the nonlinear properties of the ordinary gravity waves at the shoreline. Waves become very nonlinear, and then they excite some subharmonic resonance, and that leads to a transfer of energy towards very long periods. And these infragravity waves, they're actually very important for nearshore applications, to sea level at the shoreline, any coastal hazard, submersion, and also ocean engineering applications in which you have bodies that have tension and moorings that can be resonant at scales of a few minutes. So that's one of the reasons that as part of LabXMare we've been studying these infragravity waves a lot. These infragravity waves are also of interest to seismologists because they drive or generate seismic waves that excite the modes of the Earth. So the Earth is ringing due to the excitation of seismic waves by these gravity waves. But most of you, I guess, are mostly interested in this part of the spectrum, especially where there is most of the energy and these are the waves that you can see. Yeah. Yeah, sure. Yes. Yeah. Okay. All right. So the short answer is yes, kind of. What you have to realize is that if you want to do everything right, the infrared waves actually it comes from a nonlinear interaction of three waves in shallow water. And in practice, if you want to do it exactly, you need to have the phase, or at least the biphase and the bispectrum, not just the spectrum. And so it's people that work on these waves, either they use the spectral models with the bispectrum on top of the spectrum, or they use phase resolving models. Yet, what we've done in the code, and as part of the version that you'll be using, we've developed some parameterization to generate the free infragravity waves from the ordinary waves. And so we have some source term for that. It comes with no guarantees. We've tested it in different places. We have some papers about it. On the global scale, it seems to work working okay, but it should be a function of the slope and the bathymetry that we don't know so well. So yeah, it's first estimate if you don't have anything else, but it doesn't go beyond that. That's for the free waves, and then there's the bound waves. So the way we treat the waves in the model, and I'll come into that, we treat them as a superposition of different wave trains, so some of linear waves, but you can also compute a second order correction that goes with that. And this is actually also included in WaveWatch. You can actually post-process the model to compute the second order spectrum, and this will be the bound wave part of the infragravity waves. But we can discuss that later. So the typical spatial scale that go with these time scales are given here. So essentially, the dominant waves in deep water, they go from a few meters to a couple hundred meters. All right, so that comes from the wave dispersion relation that I'll have to show you later. In deep water, the infragravity waves, they go to maybe 10, 20 kilometers, and as you go to tsunamis, it's hundreds of kilometers and so forth. And that's typical wave spectra. And what we use to model is only this gray box here, essentially starting from a wave period of about 30 seconds, so 0.00 hertz, 0.03 hertz, so that's 30 millihertz if you want. This is 0.1 hertz, so that's 10-second wave. That's a typical peak period in the Pacific, for example. And as you go to higher frequencies, you see the energy is going down. So this is a log scale of the spectral density, all right? So this quantity here, E of F, is the spectral density of the sea surface elevation. So the elevation is in meters. So the variance of the elevation is meter squared. And the spectral density in frequencies is, as a result, meter squared per hertz. Right? So if you take the sum or the area under the curve, that will give you a quantity in meter squared. And we tend to call that the energy. And if you want to have the real energy in joules per meter squared, so the quantity of energy per unit surface, you need to take this E of F integrated times the density of the water, rho, and d, the gravity. But in short, we very often omit this rho d factor, and we usually call E of F the energy spectrum because it's easier than having one more kilograms per meter, blah, blah, blah. Usually we work with this part of the spectrum, all right, up to, let's say, 1 hertz. And yeah, and this part is the infrared wave spectrum. Usually in deep water, it's much lower. So you're talking about 30 dB difference. So in deep water, this is negligible for most applications. But in shallow water, it can be the order around. This peak on the beach, this peak is actually often higher than this one. So if you're actually measuring in 1 meter water depth, you can expect to have a very big peak here compared to this one. All right, and so the wave motion is not just the elevation. And what I want to start with is that waves actually is something that happens in 4 dimensions, so x, y, z in space, 3 dimensions in time. And we're going to reduce this motion in 4 dimensions to only 2 dimensions, and I will show you how we do that. And we will end up by essentially reducing the information, and this is how we can do some modeling with only a 2-dimensional spectrum. So to begin, I'll just introduce some notations. So what I will refer to a datum, so a reference of the vertical is arbitrary, and this is my z equals 0 level. So it can be the mean water level, it can be the chart datum, it can be the DOE, whatever you want. Relative to this datum, you have a bottom which is at elevation z equals minus h, all right? And then the mean sea level is something, so the sea level elevation, I call it zeta. And so my mean sea level is z equals zeta bar. So the bar is the average, the time average, okay? So in practice, the mean water level goes from zeta bar, which here is negative, to the actual bottom at minus h, right? So the mean water depth is going to be my capital D, which is h plus zeta bar. And this, this mean water level is going to go up with the tide and with storm surges and whatever you have. But the important water depth for the waves is really D. It's this mean water depth, which is the physical height of the water column. All right. Okay. So how we go from 4 to 2 dimensions? We have motion in the water, so motion in the air, which is right to the waves. And one very big simplification comes from the fact that the wave motion is essentially irrotational. I'm not going to demonstrate that for you, but the main reason is that the water is mostly inviscid, what we're looking at, and it's driven by pressure forces. If you drive something with pressure forces, you get something which is irrotational in the end. And as a result of that, this Laplace equation, which is now linking the so you have irrotational motion, and it's in most conditions, except for compressibility with acoustic waves or the acoustic components, you can have some divergence effect, but essentially it's irrotational and non-divergent, so you get a Laplace equation for the velocity potential. And that will reduce our 4 dimensions to 3 only, because the vertical now, if you have any motion which satisfies the Laplace equation, you can, if you write a wave as a cosine of kx with k the wave number and x the horizontal position, if you plug that into the Laplace equation, you will naturally get a vertical dependence which is exponential. That's just because of as you put the cosine to the Laplace equation, the solution gives you exponential vertically. So that is removing one of the 3 dimensions. We're only left with from 4 dimensions in space and time. We only have now 2 spatial dimensions and time, and the vertical dependence is actually fixed by the horizontal. So when you fix the horizontal variation with a weight number k, you're actually also fixing the vertical dependence, which is exponential. So that's for the water. So it's exponential kz. So it decreases vertically as you go down, and the scale of decay is the wave number or the wavelength. And if you want to look at the numbers, so essentially, if you're looking at half a wavelength from the sea surface, the reduction factor is the exponential of pi, and that's a factor of 25. So beyond half a wavelength exponential of pi, you get 4% of the surface values. And this is why people will generally say that waves that have a wavelength which is shorter than half the depth, these waves, you can consider them to be in deep water, because the bottom, what's happening at the bottom is very small compared to the surface, and so the bottom has a very small effect on the waves. Right. So KD larger than half wavelength is deep water. And actually, if you're looking at motion in the air, it's exponential up, and so yeah, the particle in the air also oscillates with the waves, and that decays exponentially. So that's true even for nonlinear waves. So nonlinear waves have the same properties. Okay. It actually happens to be the case also for when you look at compressibility correction. So if you look at acoustic waves driven by ocean waves, the same thing happens, because you have a kind of, it's not exactly Laplace, it's a you have the retardant potential, but it's essentially the same special structures, and instead of having to get some things. But it's not true when you have vertical shear in the winds or the currents. And so that's important if you're looking at how the waves are driven by the wind. And that's important also if you have shear current in the water column, that you have deviation from the exponential. But for most practical applications, and actually throughout the week, we'll just forget about this vertical shear, and we'll just work with exponential variation. So we get rid of one dimension, and the second dimension, the reason why we can actually get rid of is more or less illustrated here, is that waves are essentially linear. And that linearity reduces a lot the possible dispersion relation. And these are actual measurements from a stereo video system in which we take a movie of the sea surface which is moving, and then we can have a spectrum in 3 dimensions. We have these 2 horizontal dimensions of x and y, and then we have time. So we take a Fourier transform in all 3 dimensions, and that gives us a spectrum cube. Okay, and then we make slices with this cube, and the slices are done at a constant frequency. And so what you can see here, it goes from a frequency of 0.7 hertz to 1.6 hertz, and it's red when there is a lot of energy, and it's a log scale. So when it's blue, it means that there is 1,000 times less energy than when it's red. So it's a factor 1,000 from 0 to -30 here. And you see that most of the energy is concentrated around these curves, which is mostly, it's almost a circle. It's a slightly distorted circle because there is some current, but this is a dispersion relation in deep water for linear waves. And what we see is that actually at this frequency, the waves are mostly linear. You can see that at higher frequencies, there is a bit of something happening here. So there is some energy inside here, and these are the harmonics from the lower frequencies. So the dispersion relation is not exact, especially at high frequency. You can see that there's energy on the side here and this big blob of red here, which is the harmonics. But most people don't care about the high frequencies, and you only care about the lower frequencies and the peak of the spectrum. In that case, the peak would be even more linear than that. So for most practical applications, you can treat waves as being linear, and that linear relationship gives you a relation, which is a dispersion relation between the spatial scales and the time scales. And so in deep water, this is sigma squared called GK. I guess I have it somewhere. No, I don't have it somewhere. I didn't write it. So sigma squared called GK is a dispersion relation of waves in deep water. In shallow water, you have some punch of KD on top of that, and if you have some currents, there's also some current correction. But essentially, instead of having a 3D volume of possible waves, you only have a surface in that, which is a dispersion surface. And so you can go from these 3 dimensions of x and y in time to only 2, and then you just choose what you want. It's either you just keep the x and y, and then you get the time from x and y, or just keep some time and directions, and right. And so essentially, we can summarize the wave information as the energy as a function of 2 dimensions, and that will be our spectra. Right, so the 2D spectrum is okay when the linear, I can call them first order waves dominate. And as I was showing you, this is pretty true near the surface, and also for waves at not too high frequencies, so around the peak frequency. If you go to very high frequencies, 2D spectrum is not enough. You have this funny nonlinear correction that we like to look at. But most the people that are caring about this short waves are mostly people that do remote sensing. Some seismologists are looking at short frequency noise around 1 hertz, but other, for most other applications, just forget about that. The other funny thing is, of course, at the surface, if you do actually measurement at the bottom of the ocean, and this is one example of pressure record from outside of here in 100-meter depth. So you have the frequency here and time, and so the frequency goes from 0 to 0.5 hertz. So this is 2-second period, and this is like 10 seconds. So people that among you that do some measurements at sea, they know that if you want to measure waves with a pressure sensor at the bottom, you never can measure the very short waves. That's the usual wisdom. So it's mostly true, and actually what you see is this big band of energy here, which is the usual wind, sea, and swell band. So we can have, you actually have one storm here on September 3rd, and they have another big storm here on September 13th. But you also have this funny part here, which is actually the nonlinear pressure coming from the double frequency interaction of waves in opposite direction. And actually there is some signal in the pressure record at the bottom of the ocean for short waves. And we have some signal here at 0.3 hertz in 100-meter depth. But this is not the linear wave signal. This is a nonlinear wave signal. So if you want to interpret that, it's a bit more complicated. But here it is. So you have to be a bit careful when you're using measurements that sometimes actually the nonlinear terms are bigger than the linear terms. It's not in most type of measurements, but if you're doing measurements at high frequency at the bottom, but high frequency at the surface, there are some nonlinear corrections in there. All right. So I was talking to you about 3D spectrum and then 2D spectrum, but most applications, people have time series. And so when you transform time to frequency by the Fourier transform, you have a 1D spectrum, waves in only one dimension. And what I want to stress here is that we can usually model waves as a random process. And this is very different from the spectrum of the tide. So in this example, you have here a water level record. I think it's coming from one of the islands here, around here. And so you have measurements here for 20 days. And you can see the high tide and the low tide and high tide. And so you have here the neap tides. And here you have the spring tides around September 10. And with the tide, you can actually reconstruct most of the signal by summing just a few components by knowing the amplitude and the phase. And so here, for example, if you just take the what are the dominant components of our coast here, so it's the M2 and S2 tide, the semi-diurnal sun and moon components. You have a blue curve which is very close. Sorry, the red curve which is very close to the measurements. And this will be the tidal spectrum in which you have the amplitudes and the discrete spectrum with only energy at 6 frequencies. Now, if you're looking at wave record, actually, if you zoom in on this time series on this peak here, and you zoom in for only a few minutes, it's kind of pressure record. And here, it's not the regular. It looks a bit random. Some small waves, some big waves, some all sorts of oscillations. And you can try to build up this time series by summing a few components, but you'll never get close to it. So if you have only one component, you get this sinusoidal wave. You get two, you get these wave groups, and you can make three. It's a bit more irregular, but yeah. So essentially, the difference between the tide and the waves, except for the time scale, of course, here it's just a few seconds, here it's hours. The big difference is that instead of having a discrete spectrum, we have a continuous spectrum with energy everywhere. And on top of that, the amplitude and the phase keep changing all the time. And if you look at the measurements, it looks very random. From 1 minute to the next minute, it's not the same waves. There's no two waves that are exactly the same. Now, in the middle of all this random thing, one thing which is random but which has some predictability is the actual spectrum. So if you look at the energy and how it is distributed in frequencies, this kind of pattern, this is something that from one record, say 10 minutes, to the next record, the other 10 minutes, it will not be exactly the same, but it is almost the same. And what I should have done here is to draw some error bars on top of that, because if you take the sea surface to be a random process, essentially it's almost Gaussian. Even in this shallow water case, it's pretty close to Gaussian. If you take the Fourier transform of a Gaussian distribution, you will have amplitudes of your Fourier transform that are also Gaussianly distributed. And so, in theory, the distribution of the amplitudes, or rather the distribution of the energies, the spectral densities, are distributed with a chi-square distribution. And this chi-square distribution can have a very wide distribution, except unless you add up many different spectra. So what we take the time series, we chop it up in blocks, and we average the spectra together, and that gives us a chi-square distribution with n degrees of freedom. And as n goes to infinity, your spectral density becomes very accurate. But of course, to average an infinite number of records, you need to record for an infinite long time, and you have this uncertainty between the accuracy you have on the spectrum and the time resolution you have in your changing spectrum. So this is an example of a wave spectrum. As I said, I should have put some error bars on this, which maybe would be like a factor 2, plus or minus, because this is only over something like 20 minutes. If you can average the spectrum over a full day, the error bar maybe will be plus minus 10%. But usually during a day, the sea state has changed, especially on a tidal environment. You get low tide and high tide, you get different waves. So you always have some uncertainty in your spectra. So you have to live with that. This 1D spectrum is nothing else than a distribution of the variance of the sea surface elevation. And so the key parameter in this spectrum is not the amplitude, okay? It is the variance of your variable. So in our case, we work with mostly with the sea surface elevation. So we have the Fourier amplitude, and you take the square of that, that gives you a variance, and if you divide by the increment of unity delta f, you get the spectral density, and the sum of the spectrum is the total variance of the sea surface elevation. And yes, if the waves are really Gaussian, of course they never really are, but almost, the spectrum contains all the statistics of the process. So if you want to compute the extreme events, the freak waves or whatever, you could start from the spectrum and then compute what it is. In reality, because it's not exactly Gaussian, you can actually go to the second order. This was a paper by Typhoon which showed how to do that, and that introduced a small correction to the distribution of the wave heights, and you can actually predict the height of the freak waves if you want. Oh yeah, and I said that before, but people call the variance, we call it energy. So we usually use the letter E for this variance of sea surface elevation. So this is the average of the difference between the mean sea surface and the sea surface elevation, so the variance of zeta. The zeta elevation has units of meters, and so the variance has units of meters squared. If you want to be correct, the energy should be rho g times this, and that would then have units of joules, so energy per meter squared to the surface of the ocean. And yeah, typically the factor rho g is about 10,000 because water density is more or less this, and gravity is more or less that. So if you're working for marine energy, for example, people will work with the energy with rho g. For all other applications, people just call E the energy, and it's just meter squared. Okay. All right, so we had a 1D spectrum, but as I told you, it's not enough to describe the sea state, because even if you make the assumption of irrotational motion and linear waves, the spectrum could be 2D. So if you have frequency, it's only one dimension, you're missing something. And so what has been done traditionally is to extend from frequency to directions. And we can define the distribution of the wave energy as a function of frequency and direction. And this is normalized properly. So when you sum over all directions from 0 to 2 pi, all directions, and then you do the sum also over all frequencies from 0 to infinity, you recover the total energy, or rather the variance of elevation. So this E here in meters squared is the sum of the spectrum. So that's one example estimated from a buoy, which is not too far from here, the Pierre Noir buoy. And so here you have in color the energy density, which is normalized by the peak. And what this shows you is for each small square, which is for frequency in a given direction. So here, these are directions are coming from the west, and the frequencies go from 0 at the center. This is 0.05 hertz. This is 0.1, and so forth. So here we have a peak, which is around 0.07 hertz. That's about 15-second or 13-second period. And the energy is mostly coming from almost the west, with actually slightly west-southwest. You also have some energy at higher frequencies here, shorter waves, but you have no energy coming from the east. And of course, in a coastal area like here, with the oceans is on the west, so most of the waves are coming from the open ocean from the west. And this the variable, the frequency spectrum in frequency and direction, is actually the state variable of the wave model. So we're going to have an equation that tells us how this spectrum evolves in time and space, and how it is fed by the winds and the braking and the bottom friction and all that. So this frequency directional spectrum is really the key variable of the wave model. It's what we work with. And the difference between the spectrum and the real sea is, if you actually want to reconstruct the real sea, you need to have the phases. And when you do the Fourier transform, you have the amplitude. From the amplitude, you get the energy. But the phases, we just throw them away, because for waves, the phases are mostly random and they're not important for practical forecasting. Unless people are trying to do these days, if you actually have a ship or a buoy which is using wave energy, and you want to know how much the sea is going to go up in the next few seconds, then you need the phases, of course. But you don't do that with WaveWatch. You do that with a phase resolving model to be able to predict wave by wave how things happen. If you're actually only looking at long-term statistics of sediment transport or big evolution or anything like that, you shouldn't need to have a phase resolving model, because you don't care about each wave. You only care about its maximum, some statistics. It happens that for many beach applications, people are using phase resolving models. There's alternatives using spectral models with the biphase and bispectrum. That can also save you a lot of time, but yeah, if you don't care about the details of the motion, the spectrum is usually all you need. Now, the difficulty of this spectrum, so this is what we have in our wave model, and one difficulty we have is to validate this spectrum, because there's actually almost no measurement of the 2D spectrum at all. Okay, so most people use wave buoys or pressure gauges or something like this. What you do with this type of buoys is a data well, a very nice instrument. It's about this big, so it's, I think this one is 80 centimeter diameter. Now they are making some small ones with GPS, which is 40 centimeters, but mooring is a bit more complicated. So this buoy measures the motion of the sea surface. It has accelerometers inside, and it's measuring the acceleration, the three axes, so the X to the east, the Y to the north, and the up. And so that's a typical record of the buoy data for a few minutes. So this is 240, so 6 minutes. No, 4 minutes. And you can see it going up and down, and you see the wave groups, some big waves and small waves and big waves and small waves. And you can also see the phase relationship between the horizontal displacement and the vertical displacement. And you can also tell that the buoy is in fairly shallow water, not too shallow, because the horizontal displacement has a larger amplitude than the vertical displacement. So the motion of the buoy is like an elliptical particle motion, not really circular. But the only thing you have is 3 time series. And from 3 time series, you can only compute 3 spectra and 3 co-spectra, which gives you a total of 6 information at each frequency. That's all there is, no more. And actually, in these 6 information for each frequency, one of these 6 is just is essentially the ratio of the vertical and the horizontal displacement, and that is a function of the water depth. It's not a function of the directional spectrum. So from 6, you're only left with 5, and people call these the first 5 parameters of the directional distribution. There's several ways to present them, but essentially one is a total energy at each frequency, the 1D spectrum. Another one is a mean direction at each frequency. Then you have directional spreading, what we call sigma theta. That tells you if the spectrum is very narrow or very broad at each frequency, and it's called sigma 1 because you can also compute a mean direction and a directional spreading a slightly different way, and that would be a theta 2 and sigma 2. And so you get these 5 parameters, and from these 5 parameters, you're trying to reconstruct a full directional distribution, a function at each direction. And so if you have a directional resolution in your spectrum of, say, here, 5 degrees, it means that you have 72 numbers to invent from only 5. So of course, it's not well enough determined. And when you go from the first 5, what the buoy is measuring, to the spectrum, you're actually making up, you're inventing things that the buoy didn't measure. And that's life. If you only have one buoy, you only have 5 parameters. And so when you're trying to compare the model and the buoy, one thing to do is probably not to compare the directional spectrum itself, but rather to compare these measured quantities and not these estimated things in which things are made up. To go from these first 5 to the full spectrum, there's different methods that I've, so here I applied what's called the maximum entropy method. There's maximum likelihood method, there's other things like that. So people that do seismology have also fancy ways of going from array measurements to a directional distribution with the azimuth and everything. Another approach would be to, instead of having just one buoy, have 2 buoys, and then you have, instead of 3 time series, you have 6 time series, and you have 6 spectra, and many more code spectra, or 3 buoys. So people actually have tried that, to have something with 3 buoys connected. It's a big mess, and nobody's using it, so it's hopeless. The other real alternative is to have an array of bottom pressure records, or if you have a tower, you can have an array of wave gauges or pressure records on that, but it's not a very common measurement, and so most people actually never measure the directional spectrum. We only measure these first 5 parameters. So when you're thinking about how good is a model compared to the measurements, make sure that you rather compare the model to these parameters. And of course, the spectrum like that is nice because it tells you where it's coming from, what it's looking like, but there's a lot of invention in this shape of the spectrum. All right, so I talked about the spectrum of the sea surface elevation and its directional spectrum. But maybe most of you are not so much interested about the elevation itself, but on what happens at the bottom, which is the case of Florian with his seagrass on the bottom, and you want to know the orbital velocities and if the sediment is moving. So what you usually want to do is, okay, I know that in theory my waves have this 4D structure. I can reduce them to 2D, and actually there is a link between the bottom orbital velocities and the surface elevation, and this is given by linear theory. So with linear theory, if you don't have currents, you have this simple relationship that the orbital velocity at the bottom is the amplitude at the surface times this function, which is a function of the depths. And so at the bottom, this kz plus kh goes to 0, so cosh is 1. And so you have this 1 over change kd, and then you get the bottom velocity. So that's true for the velocity, vertical velocity, the surface slope, the pressure, all the variables that are affected by the waves. You can write their linear transfer function from the elevation amplitude A to another amplitude, which is the amplitude of whatever you want, so bottom velocity or something like that. And so you can write the your quantity as a transfer function times the elevation, and that's for all the linear stuff. And then it means that you can actually also compute the spectrum of what you were interested in, which may be the spectrum of the bottom velocity. And in that case, your spectrum of velocity is the spectrum of the elevation times the modulus squared of the transfer function. All right. So if you want to know the bottom velocity spectrum, you just take the surface spectrum, multiply by this m here squared, and you get the bottom spectrum. And then you can compute the statistics of the bottom velocity, the extremes, the 1/3 significant velocity, and all that stuff. And that's the right way to do it. The reason why I'm insisting on this is that a lot of people are computing bottom properties from just the wave height, the peak period, or some other funny parameter, which can give you a property, but if you have a funny spectral shape, or so you will never get exactly what you want. So if you really want to want bottom stuff, you have to do it this way. And actually, this RMS bottom orbital velocity is one of the output variables of WaveWatch. So instead of working with HS and TP, you'd better use just the orbital velocity coming out of WaveWatch. This is what I wanted to say. I also have to warn you about a couple things in presence of currents, and of course here we have to be careful about it. Is that the buoy usually is moored to the bottom. Sometimes they drift away, but it's usually unwanted. And so we have a frequency of the waves which is measured, which is different from the relative frequency, which would be the frequency in a frame of reference moving with a current. And this frequency is actually the frequency which is used in the wave model WaveWatch 3. And the difference between the two is that, okay, so that would be the absolute frequency of a fixed buoy, omega is 2 pi f. And this is this one, sigma, which is 2 pi, this relative frequency. And the difference is a Doppler shift by the current. So K is the wave number, and U is the, let's call it the surface current for short. And then if you want to know the details, it's not quite the surface current, it's some convoluted profile of the current. But right now in WaveWatch, we're only using something which is like the surface current. And so you have this difference of Doppler shift. And so if you're comparing buoy data with the model output, you want to make sure that you're doing the proper comparison. And at some point, we wanted to have the post-processing be able to, we didn't do that. So they are different. All right, so this is what I was mentioning before. So another example here, these are measurements of, for a few minutes, of, okay, so in blue and red you have the velocity in the east and north directions, and in black it's the pressure converted to water elevation. So it's pressure at the bottom in meters. And from these things you can compute the surface spectrum. So you have the case of the blue is a spectrum from the pressure, and the dashed is a spectrum from the velocity. And to get from the velocity and the pressure to the surface amplitude A, I use this transfer function. So if it's a spectrum, you have the transfer function squared, and it's just an example of showing that you can actually compute the surface elevation from the pressure or the velocity at the bottom. And if you combine the pressure and velocity, you can get a directional spectrum, just like with the buoy. You have 3 time series, 3 spectra, 3 co-spectra, 5 parameters. You crank that through the MBM estimator, and you get a directional spectrum. All right. There's other ways to measure waves with radars. We played with that quite a bit here in Brest. I won't say many things, but this typical SAR image, and you can actually see here some white and black lines, which are the crest of the waves. And if you make a FFT of this, you get a directional spectrum from the radar. And we know theoretically how much the change in brightness in the radar return is related to the surface elevations. We have another transfer function to go from the roughness image to the elevation map. It works more or less okay, and we're getting that pretty well. And yeah, oh, these slides were from 1.5 years ago. The Sentinel-1 is actually now up and running. So we have beautiful swell data across the Pacific from Sentinel-1A, and including in the ice. So maybe I'll show tomorrow some stuff about waves in ice, Sentinel-1A. And we'll be working in the next couple of years. So it's going to be a French tiny satellite launched in 2018. It's going to measure the wave spectrum with a real aperture radar. It's not the SAR. And the benefit of the real aperture radar is that it will also be able to resolve shorter waves down to wavelengths of about 70 meters. So it's still long for the Mediterranean, but it's much better than the SAR, which is usually limited at 100 or 150 meter wavelengths. And that will be in 2018. It's going to fly on the Chinese platform with a radio, with a wind scatterometer and this wave radar instrument, and we'll be involved in that processing of that data. These are some other example of spectra from around these are the Channel Islands in California. So the colors are wave heights from the SAR image, and you can see the island here, and these are 2 spectra, one from the radar processing, the other from the buoy, which is somewhere around here. And in these nice cases, it works really well. So what I want to say about spectra, in summary, is that the spectrum represents a 2-dimensional distribution of the wave energy. The fact that it will reduce that to 2 dimensions implicitly assumes that the waves are essentially linear, or that we have transformed the nonlinear waves into linear waves. This 2D spectrum gives statistics of the full 4D motion of the wave field if you assume the following: that the waves are linear, irrotational, and that the wave field is homogeneous. And the last bit is if you look at a coastal area in which waves are turning around, you get a spatial spectrum which doesn't match the frequency spectrum. Anyway, one caveat here is that the buoy actually do not measure a 2D spectrum, but something like a 1.5 dimensional spectrum. What I mean by this is that at each frequency we only have 5 parameters only, and so you have to be careful about that. It's almost the same with ADTP that have this funny wave modes. So potentially it says that it can go like an array processing and can go to higher resolution, blah blah blah. Well, the comparison that have been made of buoy or arrays compared to ADTP processing show that in practice, the moments are okay, but the details of the 2D spectrum may not be that great. Yeah, the linear wave theory gives you a simple transfer function from something like elevation to bottom pressure, or the velocities to the surface elevation. And this is why you can or can't measure the waves with a bottom pressure recorder. But again, if you're only interested in sediment properties, it's you don't need to go from the bottom pressure to the surface and then back to the bottom. Just stay at the bottom and transform the bottom pressure to the bottom velocity, and then you have a very good transfer function. And finally, yes, it's possible to compute some nonlinear corrections to this linear world. It's easy in homogeneous conditions, so a flat bottom. We can transform theoretically the wave spectrum to also know what should be the harmonics. Of course, in a sloping bottom and varying conditions, it's much more complicated, and this is where you typically have an effect of the phase information. And if you want to know, there's some very nice papers recently by Janssen and Herbert about what happens around caustics in currents and stuff like this. Yeah, in non-homogeneous conditions. All right, so that's all I had for the spectra. Any questions? No, not me. I don't do frequency. But in version 508, there's a space-time extreme. There should be something in WaveWatch soon to be able to compute space-time extremes more easily. I don't think they put that in this 508 version. So there's a couple groups that are working on it. Okay, so there's people at Georgia Tech. So it's Alvise and ISMA, Alvise Benitazzo at ISMA in Italy, and Francisco Fiedler at Georgia Tech are working on that with NTEP to have some package in WaveWatch to be able to compute the space-time extremes. What we have in WaveWatch is a second-order correction from Peter Janssen to be, and that's more used for computing the bound harmonics and things like this. But if you're brave enough, you could look into that and try to go back to this 2009 paper to compute properly the BFI to get the. Yeah, I'll let you do that. But yeah, I'm not doing it. But yeah, the extremes are related to these nonlinear corrections and possibly other things. There's a still debate between people that say that it's only second order correction. Some other people say, well, there's also some third order breathing KDD type behavior of the nonlinear evolving wave groups. But yeah, different groups don't quite agree on what it should be. And to me, if you actually look at the Typhoon paper from 81, it really reproduces pretty well the distribution of wave height. So I don't think you need to go beyond that, but I am not the expert. So, any other question about the spectra? So yeah, I hope that for most people it was not a big discovery. Actually, it's still the same part of it. So yeah, don't worry, it's part of the same slides. Oh, you want to break? Yeah. Right. Okay.